maybe I shouldn't say this out loud, but you know, if you just make a reasonable contribution to the class, everybody should get an A.
Okay, that sounds fair.
Also, can I like officially sign up for a time to present?
Yes.
Like, could I, like, if I
That's
say,
too
could I do
formal.
next Tuesday? Could that be my, or, which, like,
Okay.
is that okay?
Okay, so next Tuesday is Wrigley's Day.
I just want to set it in stone so I can like finally just put together. Okay, yeah. And if I want to like,
Is something about geometry?
yes, it's
sort of.
about it's like two different like a linear algebra and differential geometry approach to like some geometry concepts we've talked about.
Okay.
And I could send because I have like I'm gonna make like an outline presentation, but I'm gonna do a lot of stuff on the board. So would you want me just like to email?
I can wait until your actual presentation.
Okay.
That'll be fine.
That's okay. Awesome.
If you remember absolutely nothing, well, maybe not absolutely nothing, but if you barely remember vector calc, it's okay, because I'm trying to simplify it. Because these things, I think we can all agree, look pretty ugly.
What do you mean?
And of course that's an aesthetic statement, so maybe you think they look really pretty, but, you know, it is in the eye of the beholder, I guess. But, I guess, today I'm going to try and revolutionize the way that you look at calculus. So that may sound like a daunting task, but I hope that I can do that. And it's kind of like this. You know, I mean, I think we've all seen this. And there's kind of two ways of looking at it. I mean, you can say, you know, e to the I pi, it's -1. You know, e to the I theta is cos theta and psi sin theta. Like, that's what it is. You know, You can also look at it and be like, the number defined by compound interest, and then you raise it to the power of the square root of -1, something that really shouldn't even exist intuitively, times, you know, the ratio of a circle's circumference with its diameter. What is that? Well, it's -1. You know, so I mean, there's like this two ways of looking at math where you can be like, whoa, you know, that's really profound, or you can just, you know, you'd be like, it is what it is. So maybe some people will see this and think very pragmatically and be like, it is what it is, but I think it's a very beautiful piece of mathematics, and when I saw it, I was like, it changed how I looked at calculus. So, does anybody know the names of these theorems?
Fundamental theorem of calculus.
Fundamental theorem of
The
calculus.
second one, is that like the Jacobian times the cross product with, I feel like that's from Calc 3.
Yeah, these three right here, they're basically the punchline of Calc 3. This is Stokes' theorem. Okay, this one is another man with the last name. Do you remember? Anyone remember? It's a color.
Gray's theorem?
Close.
Yellow's theorem.
You had G. You were good with G.
Green.
Green's theorem. And this one is probably the most intuitively named. If you know what this thing is called, then you know what the theorem is called. It's the divergence theorem. So this is divergence.
Yeah, it also has a name, a named person.
Oh, does it?
Yeah, Gauss's
Oh,
theorem.
Gauss, yeah. Another G. Yeah, I forgot about that / didn't know that ever maybe. But anyway, divergence theorem / Gauss's theorem. So I don't know, raise your hand if you want to memorize all these and think they look really nice and easy to remember. I would probably...
Surely they're all completely different.
So, star student, or everybody else, what do you see, what common properties do you see in these four theorems?
Integrals in all of them.
And there are integrals in all of them, so they involve integrals.
Differentials.
They involve differentials. D for differential. Any other commonality?
They're over some region.
They are over some region, okay. So, right there we have the ingredients of an integral, right? This is just notation. An integral is really a function that takes in, well, a function and a differential. Maybe you want to say like f of x dx and then some region, or you know, this right be part of the definition of the region. It's a little vague. I'm going to try and you know, make that clearer. But apart from their ingredients, is there anything conceptual about them, maybe about what they're saying that you can spot?
Another element is a boundary.
That's an important ingredient. Yeah. So everyone's seen this. You've probably seen it to mean partial derivative. But we also use it to mean boundary. So right here, this side is integrated across some arbitrary surface in R3. This is integrated across its boundary. Okay, so maybe let's do a rudimentary example. Let's say I have a ball. In math, I think you're supposed to differentiate between ball and sphere. So the ball is the whole thing, a ball, right, that you can hold. What is the boundary of the ball? If I stick dv on that, what's another name?
Sphere.
The sphere, right? So if this is like a three-dimensional ball, the boundary would be S2, right? Okay, how about the disk? And well, I can kind of, so ball would be the whole thing, sphere would just be the outside. What about the disk in the plane? What would the boundary of the disk be?
The circle.
Circle, so you can call that circle, or you can call it, usually you call it S1, so one-dimensional sphere. So, okay, we've got four theorems that have integrals, regions, functions that you integrate over, and somehow we're involving the boundary of the region in this. We're going to come back to that, but what if I told you that there was a way to write all four of these at once? And it's easy to remember too. It's not like some gigantic, enormous mess. You just have to sort of redefine the integrand, essentially. So, what if I said integrand? What's an integrand?
That thing.
The thing in
The
A
S.
function.
Oh, the thing
It's
in
the
it.
thing inside the integral.
Right, the thing you're integrating.
You're right.
So the function, right?
Yeah.
So usually we think of this
See.
as something like this, right? This is the integrand f of x dx times dx. And you know, that gets you pretty far thinking of it like that. It's like a function and then you multiply by a tiny little step, and so you're basically adding up areas because it's some height times some little width, and that's how you think about it. Or if you think about it in higher dimensions, it's like cutting up some shape, right? And these are the little steps, okay? There's a different way to think about what the integram really is, and let's start in R2. What are all the possible integrands you could write down in general? If I have, and to be clear, this is a function on R2, so we're talking about like, so it really lives in R3, right? The height, it's a three-dimensional function of x and y. See what I mean? So
The graph is in 3D.
yeah, the graph is in 3D, but we're integrating over the plane. So in general, you'd have some f of x and y, right? But what are the possible measures or differentials that you could have, that you could tack on?
dx or dy?
dx, yeah. So you could have f of xy dx. You could have some g of xy dy. You could add them together. Is there another possibility?
Can you do like a double integral and have dx and dy like go on the same function?
Yeah, so dx times dy. So, and that's some new function, maybe h of xy. So these guys are like little infinitesimal segments of a line, And what does this represent? If these,
Infinitesimal, like little squares.
yeah, little areas or squares. So like, that would be like, I'm just gonna draw a line, and then little square. Let's go to R3. Functions on R3, the thing lives in R4, we can't really visualize that, but it's functions of 3 variables. So, f of x, y, z, what are the possibilities?
Have dx or dy or dz separately.
Yeah, so I'll sum all the indistinct possibilities for the lines, segments, or what have you. And then what are the possibilities for the area element?
dx dy, you could have dx dz, you could have dy dz.
Dx, dy, dz, or dx, dz, and I'm running out of letters, but, you know, you can add those together as well. And what's the final possibility?
All 3 at once.
Yeah. So something times dx, dy, dz, and what does this little element represent?
Like a prism type thing.
Yeah, a little cube.
Cube thing.
Or, you know, it doesn't necessarily have to be orthogonal.
Did
Some-
you just say Z?
I've gotten in the habit, and I don't know if it's, you know, more, you know, faster or not, but.
I think it's cool.
Yeah, well, anyway, yeah, that's a British thing. On instead of over. On does save a lot of time. Over is 2 whole syllables, you know. So anyway, the way that you're constructing these integrands, does that remind you of anything?
I want to say combinatorics, like where you have all the combinations, but also order doesn't matter here. So
Okay.
I kind of take that back.
I think you're closer to the answer than you realize. Anybody else? Any thoughts on what we're kind of doing with this and this?
You're multiplying.
Yeah. And then you're adding.
Oh,
And then you're at-
this is like a linear equation with scalar, or what am I thinking?
I think
Combination?
Linear combination.
linear combination. You're taking linear combinations of f's and d somethings. And where do we take linear combinations of things?
Linear algebra.
Yeah, but in what mathematical setting?
We do it with like everything, don't you? You can do it with real numbers or with polynomials
Mhm.
or matrices.
Yeah, you can.
Yeah.
Yep.
Yeah.
Um,
I know. That was not a good answer, but
no, it was a great answer. What do you call that?
which one?
Math.
Vector space.
With this collection of objects?
No,
Yeah,
vector space?
it's a vector space. It's a collection of objects that you can take linear superpositions of. Okay, so
Okay, so with the vector space, you have the set of the vectors, and then you have a field, which are you use for the coefficients of the linear combination.
right.
But here, which is which?
So these are considered like the scalars,
Okay,
and this is like a basis. So let's kind of formalize this. In R2, we have dx's and dy's making a basis, right? And then there's another basis of not only can you take superpositions of line segments, that's kind of how I think about it, but you can also take superpositions of little areas. So not only are you doing this to make this, but you're kind of adding up little squares. And you could think about it like in terms of a normal vector turn into a vector, but and there's a whole sort of way to think about this more formally, but I mean, you get the picture. There's only one of those guys in R2. Okay, so what's R3 look like? What's the basis for line segments?
dx, dy, dz.
Yeah. Dx, dy, and dz, right? What's the basis for superpositions of areas?
dx, dy, dy, dz, and dx, dt.
Okay, what's the basis for superpositions of volumes?
All three together.
Yeah, there's only one possibility. The dx, dy, dz. Okay. So there's a way to, maybe I should have written like, okay, how the other one you can add is the trivial one of just scalars. So you can add together scalars in all of them. And perhaps I'm not being very formal here, but I want you to see something here. So how big is this basis? All right, R2. How big is this basis?
1,
Yeah, it has one element. How many elements are in this?
2,
How many are in this?
1,
Okay. How many here?
1,
How many here?
3,
It's
How many here?
It's the thing.
3,
How many over here?
1.
How many if you're just?
No, it's Pascal's
Pascal's
triangle.
triangle.
Huh?
Wait, but but, okay. Never mind, go ahead.
R1, you can only take combinations of scalars in one possible line segment. You can only take superposition of points, superposition of scalars. Okay? Now, if I were to ask you that question in R4, you'd probably have to think about it, but can you just tell me? How many scalars?
1, 4, 6, 4, 1.
One. How many line segments? Yeah. How many areas?
Yep.
So that is a combinatorics problem. And this is, I believe you call this a Grassmann algebra. There are further fancy names for geometric algebra, and they both have different axioms. But basically the idea is not only are you taking superpositions of oriented line segments, you're also taking superpositions of the higher analogs. An oriented area, an oriented volume, an oriented hypercube. I draw a hypercube. I'm not going to draw a hypercube. But anyway, that sort of picture is what's going on geometrically with the algebra of integrams, you could say. So it's called they're called differential forms. So this is a 1 form. It only has the line segments. This is a 2 form. It only has the areas. This is, can you guess?
Oh, 3 form.
3 form. Okay? So let's try and make the integral more satisfying, perhaps. Write it differently. We're going to call, we have a new variable, omega, or omega.
Oh my god.
That's another British thing. This could be any k form, okay? So if you're integrating over R2, k runs, how does k run?
Fast.
Just 1.
Yeah, there's a 1 form, there's a 0. So a 0 form is just a scalar. So, and that's, and maybe it doesn't make sense to have an integral over with no measure, but I'll talk about what that means.
So that would be just like evaluating a function at one point.
Boom, yeah, and so maybe you see where the fundamental theorem of calculus is coming in. Okay, so you have a 0 form, you have a 1 form. What's left?
Ew.
2 forms, that's it. You can't have 3 forms in R2, right? I think you get the picture, 0, 1, 2, 3. So, what we do we don't integrate functions with differentials, we integrate forms.
Okay, time out. Can I ask a question?
Yeah.
On that K, so those are just all the types of regions you can evaluate over?
Exactly.
So point, line, plane for R2. and then-
Exactly.
Okay, okay.
Point line plane, or point line square cube,
Mm-hmm.
et cetera, et cetera.
Sorry, yeah, it's just, yeah, you're right.
Okay,
Cube, yeah.
so this guy you should think of as being this. It's a variable that catches all the stuff you would want to integrate over. Okay, so it's just none of this messy D, blah, 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 little circles and dells, and I'm just integrating a form, okay? So now we have to introduce the concept of what is the integral's counterpart? What are all these things? You know,
Right. Kinds of derivatives.
yeah, types of derivatives. You know, screw all that just deep, okay? This catches everything about those once we've defined it on forms. Okay. Let's do that.
Does this accompany the functions at all? So omega, it takes the region and the functions together. It's one thing.
Mhm.
And the same with the derivative. Without, okay, yeah. Okay.
Right. Repeat that. I think I know what you're saying, but.
That omega is all encompassing. It's the function and the region together.
It's the function, because it's the function and the integration measure. I shouldn't have
okay.
used those interchangeably.
So like if it could be a function and the square, something like that.
Yeah. So, recall what George here. I didn't know the level of formality. Anyway, what does an integral take in? In this case, it's a form and a region. So you're still going to have that region. We've only done half the picture so far. You're still going to have that region under here.
Mm-hmm.
But this guy is absorbed into there. Does that make sense?
So okay, yes.
So this still tells you what you're integrating over, but the little d's kind of tell you how you're doing it, if that makes sense. Because
Yeah.
like integrating over
So it doesn't so the omega doesn't bound what you're integrating. It just shows you what you're integrating over.
yeah, exactly.
Okay. Yes. I
Yes.
got you.
Okay, so if you were to implement this thing as a limit of Riemann sums, would that omega tell you how to index the sums?
It would be the function, and it would be the little delta xi, right? The delta xi's would be.
Yeah, so it would tell you, do you have a single sum with a delta x, or do you have nested,
Oh,
double
right,
nested,
right,
or
right,
triple nested?
So this would correspond to 1. This would correspond to 2, which would then correspond to 1 integral or double integral. But the thing is, it's implicit in the omega. So all you have to do is write this. And then if I tell you that this guy is this, implicitly you know to evaluate it like that. Okay, we have a function. That's the easiest case. We're going to start in R2. I want to construct df. Does anybody have any ideas about what that would look like as a superposition of differentials or combinations of differentials?
The gradient?
It is the gradient, yeah. So what does that formula look like?
df dx, df dy.
Other people, perhaps? No offense. I know your stuff.
Yeah, I'm my instinct when I'm sitting in a class is to be
Yeah.
answering the
mi-
question. So,
Mine is too.
Okay,
So,
can you repeat the question?
so I've got an f, but let me say it like this. So if I have a scalar, which are like my f's, right?
Mm-hmm.
The operator d is going to take them to a what? Like what we're calling a vector. So something dx plus something dy, etc. Or if you want to be fancier,
Are you implying it's the plane or something like that? Is that what
It's a
you're saying?
gradient, is what he's saying.
Oh.
well, what I'm saying is d takes in a k form and it spits out a k plus 1 form. Okay? So you take in a point, you get a line. You take in a line, you get a square. And if you want to use the correct notation, 0, then you use this. So this is whatever, n probably. So this is 0 forms on our end. You hit it with d, you get 1 forms on our end, etc., etc. And if that notation is too abstract, don't worry about it. I'm just taking a k form, hitting it with the operator d, spitting back out a k plus 1 form. So if that seems vague, apply it. This is a point. This is just a scalar. I'm going to hit it with d, apply d to it, and what am I going to get back out? Something with sums of d, right? So it's going to be something dx plus something dy. What should go here, though?
Yeah.
So it should be just f of x on both?
F of x, y on both of them.
No, it should be the, wait, no.
You're close.
Are you saying like f of x with dx and f of y with dy?
No, because it's still one.
I think you want to say sub, indicate a subscript.
Oh, like the partial
Oh.
derivative?
Boom.
Gotcha.
This is just the multivariable chain rule. You could divide by dt, whatever. You know.
And if you write those things with the curly df over curly
Perhaps
dy,
it might look more familiar.
Right.
so then you can do that Leibniz trick of pretending those are little fractions that you can cancel.
Yeah. So it's actually very intuitive, this subscript note. What are you doing?
I'm writing those again.
Get out of my teaching area. So,
I'm not going to the bathroom, I was just too excited.
so this is an intuitive way of writing it because it's like the projection of f onto the x coordinate. So like, you're taking a derivative with respect to x, just x, right? That's what the partial derivative is. Or you're taking derivative of f with just y. So they're like, it's like components of f. So it's a component of f times the x basis vector plus a component of f times the y basis vector. And you can do that for R3. So what f is a function of what variables in R3?
X, Y, Z.
Okay, what's df gonna look like?
Well,
Partial with respect to each, and then the differential.
yeah.
Does that make sense? So, and this, and you said it, this is a vector calculus object that we usually write the gradient of f. But we're going to forget about those cumbersome upside down triangles and just write it d something, df defined to be this. The partial derivative of the thing with respect to each coordinate times its corresponding differential. Okay. Now, how in the world do we do that for two forms? So, omega is going to be a two form. Okay, or let's not be confusing. Okay, so what's a two form going to look like?
So you have the double partials, right? So like the ones like dy dx.
Right.
Yeah.
Right.
Double.
Yeah.
Okay, well, so it won't be partials, but it will be the differential. So.
So that's sorry. Yeah, that's. Yeah.
But I think that's what you meant. So, something times this plus something times.
D, y dt, and then dx dt.
Okay, now let's just say that it has some components a, b, c. A, B, and C are understood to be all functions of x, y, and z. A dy dx plus B dy dz plus C dx dz, that's the most general two form you can have in R3. Okay. Now, let's say that this is omega. Now I want to figure out what d omega on this is, which is a little more complicated. And you could maybe think of defining it in a few different ways. You might think about, well, take the multivariable chain rule and then hit it with another derivative. But the way we're going to do this is, again, it's going to have a more geometric intuition. So if d something is a little oriented area, what do you think, what would dx look like?
Like a square, right?
What though, because you have dx as a little segment in this direction. What's the area spanned by dx and dx?
Oh, 0. It's the same
Nothing.
thing.
So these go to 0. Okay, that's the first rule. You could call this an axiom if you wanted to be fancy. Well, let's see here. If I flip these, how do you think they should be related?
Opposite?
Yeah. So this is dx dy. I'm going to flip it, and it's like the negative. Because if
Yeah,
you...
so it's like the right-hand rule.
Yeah. dx minus dx. dx dy, flipping it, gets you the minus of this. Okay, and if you can also think about it as having a little normal vector. And if you flip the area, what happens to the normal vector?
Inverts.
Inverts, turns around. Yeah. Okay. This is enough to define this. What we're going to do is take partial a with respect to x, and then hit this, or this is not what we want to do yet. So we haven't actually done this. Okay. So derivative of a with respect to x, this gets a dx tacked onto it. What? This gets a dy tacked onto it. And what happens to this term?
0.
Goes away. Okay.
Where did the dy come from?
So every time,
Oh, because you're taking partial with respect to y?
yeah. So basically, look at this like its own little zero form. Hit this guy with d, or and then you have the extra dx, and
Right, so the A is like f of x, y.
yes, right,
Okay.
yeah. Would it be more helpful if I wrote FGH or something like that?
No, it's
Or-
okay.
I didn't,
okay.
no, it's fine.
Okay.
I was just wondering what variables each one we were looking at.
Yeah. So then what would be the last a term?
dx dz
Or
well yeah with that.
dA, dx, or dy, dy.
What? No, dx dz.
Oh.
Yeah, so all these are going to start with dx and have the different differentials come in.
Okay.
But the one with itself always goes to 0. Let's do it for b, okay? Tell me what to write.
dA,
B?
db, d,
X.
you can go x.
Yeah.
dy,
dy dx.
Perfect.
And then dA, dy, db, dy, and dy, dy. And then db, dz, dy, dz. And then the middle one leaves.
Okay. What about c?
Same thing, but
Same thing,
dz,
but
dz.
dc
It's
dx,
gonna be dz, dz.
dz dx,
And then
dc dy, dz dy, dc dz, dz dz. Which one goes 0?
the last one.
Boom. So you get this. This might, yeah, it looks gross now, but this is actually something you're used to. So these middle ones go away. How are these flipped? All the rest are just flipped things now, right?
Oh yeah, so
Is
the
this a
negative
metric?
ones cancel.
Not quite. But
Oh,
we're good.
so you're gonna have this partial minus that partial.
Yeah.
So don't say it. Don't say it. So this, I'm going to put a minus sign here and flip these.
Yeah.
I'm going to
Do it with
Put a minus.
dydz and dxdz as well.
So right here you're saying? Or
Yeah,
you did that one?
that one that you just did, and then also the one in front of it. Yeah. then
And I may have minus signs off because one dx, dz, one of the orders that you don't expect might be defined to be positive. It doesn't really matter.
I'll be back in a sec.
Okay, well, you know where I'm going, I think.
in
Yeah.
factor.
Okay,
I
so
don't know.
it's kind of like factoring.
You want to put the dx's and the dz's and the dy. You know what?
I know what you're trying to say.
You know where I'm going.
Let's try and write it as a vector dotted with another vector.
No, I don't like that option.
Well, it's just this thing times this thing, plus this thing times this thing,
Okay,
plus that thing times that
well,
thing.
that's fine, but I don't know how to do
You
that.
said this whole thing is just a dot product?
Of two things, yeah. Two things that you're gonna recognize.
Oh,
So this does
Yeah.
look like a dot product. Ugh.
But it's not just any old dot product here. Okay, so let's collect terms. What is the dx dy term?
dA, dy, and then negative dB, dx.
What is the
Ooh.
dy or dx dz term?
dA, dz, and negative dc, dx.
And what is the dy dz term?
The
Oh, awesome.
dB, dc, and negative dc, dy.
Does this look familiar?
Yes, but I don't remember where
So
from.
these guys are going to be components of a vector, and
Oh, yeah.
maybe it will be cumbersome to write them all again, but I'm just going to write them as an ordered pair vector thing, components. Minus dc dx, db dz minus. And then dotted with dx dy, comma, dx dz, comma, dy dz. Okay? And handwriting is probably something I'm going to have to work on, but this thing you call dA, that's just the unit, that's just renaming this. It's a vector with components dx dy, dx dz, dy dz, all the basis vectors, just like this. So that makes a little more sense. That's just the thing pointing, you know, in all of the basis things. So that's what that
Is
is.
there a reason you chose A for that?
Because what do these represent? And I know I used A, so I'm using notation, but I could use S.
Square.
Okay. I just thought, I didn't know if you meant the same thing as like the region A,
Well,
or like the A that you sort of defined earlier.
it's associated to that. These are areas,
Yeah.
right? So this is a little area vector.
Okay. So
Or-
it's not
or-
the same as like the function A.
No.
Okay.
Yeah. That's probably where I was confusing. But and these are the components of okay, what we could call, and I probably should have done like AX, AY, because I could have just called them all components of one thing, you know what I mean? But we'll stick with what I put. So A, B, C. Should have thought of notation
Big
there,
F.
but
Yeah.
big F.
Vector function, big F.
That works. Big F. So this is the curl of F dotted with DS.
Something that made us see.
So let's summarize here. Gradient of F, that's just dF. Curl of a 2 form is just the omega, one form. So if you hit a scalar with D, you get the gradient. If you hit a vector with D, you get the curl. And there's an analogous thing for, maybe if you want to talk about the divergence. I'm not going to quite go there, but I invite, exercise to the reader, all that, because it's pretty satisfying. So let's just do it with Stokes' theorem. Okay, so anyone remember what Stokes' theorem was? No, of course not. It's this. How can I rewrite this in my new language? And sorry, I should have. So d omega for a 1 form. When we integrate that over some region, the fact that the little dx dy's are attached to a 2 form, if we understand this to be a 2 form, I could call them 2 form, I'm so sorry. Oh, it's a 1 form. Omega is a 1 form. D omega is a 2 form. Omega is a 1 form. But okay, there are little dx dy's attached to this thing, so that's implicit. That implies the 2 integral bars. We don't need to write that. But how would I write this side? So if we started with this.
Is that S vector or not?
Well, this isn't a vector.
No, but I meant the vector we had at the bottom.
So that the vector that we finished with right here, that's this.
But I mean the one
Yeah,
on the
so
right.
should that A on the right side be an F?
Yeah, I'm sorry. I should have thought about notation better. Yeah, that should be enough. So this is going to be integral over the boundary of S, we know that. And then if I have this thing just looks like this. Because DL, I wrote R here, but DL is dx dy dz, and then you dot F, which is we were calling ABC. If you dot this with that, you end up with just omega, right?
So it's like that curly D moved from in front of the omega into in front of the S.
Yeah. So if you don't completely follow that derivation, it's fine. I invite you to try and justify it for yourself, that you can rewrite all of those formulas like this. Let's do the fundamental theorem of calculus. The fundamental theorem of calculus itself, what kind of form is that?
It's,
One.
That's a one form. And I'm going to rewrite, instead of putting AB here, I'm just going to write over the interval AB. Okay? And this evaluation, so, okay, well, maybe let's do this. What's the boundary of an interval?
It's
So if this is my interval, what's its boundary?
I guess I would say the two endpoints, but one of them has to be called negative. I guess. I don't know.
Yeah, that follows from the switching convention, I think. Like if you switch the interval endpoints, that's just like switching dx dy. It's analogous to that. Is that what you're kind of talking about, or?
Well, I'm trying to anticipate, why one of those has a minus on it.
Oh, right. So integration. Well, okay, we'll get to the boundary. So the boundary.
Okay. Also, in your statement above there, the equation above there, should that be d big F dx, or did you? Or
You could rewrite it like that. So
was that supposed to be a lowercase f there?
this is a lowercase f, yeah.
Okay.
But I mean, we'll do that here in a second. So the boundary of this is just the 2 points. Integration over 2 points is nothing but evaluating the function. And it's kind of like if you thought about it like, I'm going to add this area to this area. Well, you're just adding 2 heights. This is not included anymore. You're just doing it on the boundary. And so this becomes, yeah, so somewhere in the convention, you say that like, you take the difference of the 2, and I think it's because, like if this is f of b and this is f of a, you're really just talking about that, the area of that shape. But how would that, because, yeah, I'm not quite sure on that one, because you could, I mean, how does that apply to the bigger dimension? Like, what's the analogous way of, why should that be negative, basically? Because you're summing up, you should be summing up those 2 heights.
So maybe a point has an orientation, rightward or leftward.
That's it, yeah. Yeah.
Point on the number line.
Yeah. So, okay, yeah, because it's all oriented in this. So, like dx always has an orientation, dx dy has an orientation. So
Yeah. So the left end point points to the right, and the right end point points to the left.
That makes sense. Yeah. But anyway, this is still the fundamental theorem of calculus. What you're doing is you're saying take a derivative, f df is f, right? You're saying take a derivative and evaluate it over a surface. It's the same thing as taking the integral of the thing you took the derivative of and evaluating it over the boundary. So you can write this even more abstractly, and this is kind of where that notation comes in, where it's just like I is just some function, right? I is just some pairing between an integrand and a region, or in our new language, it's a pairing of a form and a region. Call the region R if you want, I don't know. This is the punchline. And if you don't want to think too hard about my messy derivations here, just think about what this is saying. Taking the derivative of something and taking derivative of something over a region and integrating is the same thing as taking that thing and the region's boundary and integrating. So, in some sense, you could say that the derivative is analogous to the boundary. They act on different things. The derivative acts on functions and forms. The boundary operator, it acts on regions and geometric things. But the derivative is doing something completely analogous to what the boundary operator is doing. These little r's live in their own little world, and the omegas live in their own little world. But how d comes into omega's world is completely analogous to how del comes into r's little world. The derivative is analogous to the boundary. And to quote Salman Khan, if that doesn't blow your mind, I don't know what will. So, thank you.